Okay, so like I was saying, you guys should have done the MCQ A on AP Classroom. Did anybody take note of questions that they were really stuck on that they wanted to do? Good. I wanted you to like record your responses, and then did it tell you the results right away?
I had to reload it and go back into it. It took me a few minutes.
Okay, good. So that's good. I made it so that you would see the answers once you submit it, and I wanted you to go in and like look at what you got wrong and make a note of it, and then ask me. I want to go through some of them, and we can kind of solve them together. All right. So
because our school in our infinite brilliance has installed an ad blocker that blocks AP Classroom for me. What? Like, you know the thing when they install a block like dangerous websites or whatever?
Yeah.
It blocked.
Hey, restart the computer. You know, because this has happened to me several times. Where it will block your email, it'll block PowerSchool, it'll block Google Classroom.
Really?
Literally.
Isn't there a little link at the very bottom that says like I'm aware of the danger of going? YouTube sometimes does that.
No, it says it's blocked.
What?
That's if Google itself tells you that.
No. I think it's your guys' blocker.
No, it blocks you out.
It depends on the
Because Mr. Wardinger has said, like, if you give a YouTube video in your class and the kids can't access it, there's a thing at the very bottom that says, like, okay, like, I'm aware that I'm going to a unauthorized site, which is just going to YouTube.
This was like request blocked, and there's a big red line at like 1 or 2.
Yeah.
Oh, well, shoot, I
didn't
know that was a thing. I wouldn't have expected that.
You have to reset your computer.
Just restart it?
Just hit the restart sign.
Okay.
Why?
Well, shoot.
I found a way around it.
I'm sorry. I don't know.
That's what I'm saying. These computers are garbage.
Well, they probably
Yeah,
better
replace
if they
it
weren't
and
installing
see
all kinds of
Replace
propaganda.
them
Yeah.
at the end of the year,
I'm
so
curious what they're
hopefully-
going to replace them with.
Well, since they don't make these
They don't make the
anymore,
11
we're probably gonna have to buy like a new MacBook Airs.
The 13-inch.
And those are more expensive.
Yeah, I don't know if they'll upgrade to the new ones. They'll probably get maybe some like a couple-year-old ones. Because these are, well, I guess I don't know when they bought them. But anyway.
They stopped making that model in 2016.
They
don't
change
sell
the
anymore.
technology every 3 years, and this is the 3rd year.
Yeah, and I guess I don't know if they buy new as of that day. But anyway, I'm sorry. I'm getting distracted. I need to get going on this. Multiple choice question A on AP Classroom. I apologize. A lot of it was gravity, and we're going to talk about it today. So I apologize. I didn't know that. It's whatever. But I wanted you to do this as a way to practice for our test. This is, again, harder than the test. This is full-blown AP level. But I wanted you to take note of questions you got wrong so that I can go through them. Like, Mr. H, I had no clue on this one. Can you help me out? And we'll do a couple together. So I'm going to connect here. I'll pull up the answer key. And we'll work through some of the really tough ones so that we can learn together. Yeah, A. So, does anybody have some that they know right away? Like, hey, I want to see this one worked out. I don't get that. We can work through that one. Number 7? All right, let's go to number 7. Number 7. No, give me one view. All right, does everyone see that? So the answer is A. I gave it away. So this question, we'll read it. So I got 2 circular motions, right? Object A is rotating at a radius of d. Object B is rotating at a radius of 2d. It said they're satellites. There's a centripetal acceleration for A and a centripetal acceleration for B. That should make sense. If they're going in a circle, there has to be a centripetal acceleration. What is the centripetal acceleration of B in terms of A? So what you have to start with, and again, I apologize, this one is one of the gravity questions. We'll learn about it. It's one extra equation. We're going to talk about the force of gravity is This is the force of gravity for any two objects. This is a constant. It'll be the same for everything, no matter what. The two masses, whatever objects you have, and then the radius squared, the distance between the two. So what you do is you basically do the first one and say, so A, force of A, is going to be G M A M, this is going to be M, over D squared. Literally just plug and chug. We don't know the numbers, we don't care. We want to know, okay, what's FB? Well, it's G. What's the mass of object B? Well, it's the same, right? They're two satellites. It doesn't say the mass, so it's just the same mass. So we're going to do mass A, since it's the same, and then M of our planet. Okay, I'm going to do a capital M. What's the distance of satellite B? The distance between the center of orbit and the orbit itself. It's 2D. So this is where you say it's 2D squared. Then what you have to do is you got to make this equation look like what you started with. So all I do is I say, okay, M-A-M, I'm going to make this, I want D squared, because that was what I started with. I want to make it look like that, so I'm going to pull a 4 out. Does that make sense? Now I have D squared. Well, everything is the same except for this 4, so I'm going to pull that out. Then that's my answer. This is this. So the force of B is 1/4 the force of A. What that tells you is if you keep everything the same and you increase, if you double the distance of an orbit or rotation, the force that keeps it in that rotation goes down by 1/4. Well, the answer is talking about acceleration. Well, force is acceleration, right? F equals ma. If it's just scaled by the mass. So if the force is 1/4 of the original, then the acceleration is 1/4 of the original. So that's why your answer is original acceleration over 4, 1/4 of it. Does that make sense? Even though we technically haven't learned this yet, it's literally just this equation. It's just talking about gravity. This is the full-blown formal way to calculate gravitational force. But that question was, they ask a lot of like comparison. You know, if you double the mass, what happens to the force? They really want you to know the equation and know what happens if I double this variable, what happens to the total value. They really like those questions. So that's where you plug it in and then make it look like the original, and then you'll basically have some coefficient that tells you, oh, this force is 1/4 of my original. That's what number 7 was asking. Again, really sorry. This unit is hard to get everything in on time, and so we haven't got to gravity. We'll talk about it today. It's not that bad. It's just really unfortunate timing because we got to be practicing for the test, but this had everything. We hadn't got to it, so I apologize. Is there another one that I can do for you guys? No? Again, holler at me. I want to look through and see if they're... $17? Oh, okay. It's a good one. Come on, hunk of junk. Alright, everyone see that guy? So this one, a 2 kilogram object is released from rest from near the surface, assume you have no air atmosphere, that means no air friction. You're just dropping it. A graph of the object's speed, velocity versus time is shown. What's the weight of the object? Well, what is the weight? Huh? No, those are completely different. This is mass. M is 2 kg. Yes. Weight is how gravity pulls on your mass. Well, how do you calculate the weight of something? How do you calculate the force of gravity on an object? Right? That's weight. Your object has some mass, and the Earth pulls it at a certain force. That pulling down is what your scale reads. Your weight in English units is pounds. In science, we call that newtons. It's the SI units. Well, this is just F equals ma. We know the acceleration of gravity is g, 9.8. Right? So if I know, hey, this is 2 kilograms, this is saying this is a different planet. We want to see what the weight actually is. So we need to do F equals ma. We want to know this. Mass we got. Is there any way we could find the acceleration of free fall for this planet? 4 meters per second. How'd you get meters per second squared, right?
Yeah.
Yeah, how'd you get that? The graph,
Yeah.
right? This is velocity time. Acceleration is the change in velocity over time. I literally just take the slope, right? Acceleration equals change in velocity over change in time. Well, I got velocity time. I could find the slope to tell me that. Well, I always pick the end points, right? So my final velocity is 20. I'm going to do here and here and calculate the slope. Final velocity is 20. Initial was 0. Final time was 5 seconds. Initial time was 0. This equals 4 meters per second squared, right? 4 meters per second per second. Well, we know free fall acceleration of this planet. 4 meters per second squared, 8 newtons. So we can use F equals mg, right? Newton's second law. We got velocity time. Well, the change of velocity over time is literally acceleration. I could calculate this planet's acceleration in free fall because it told us we just dropped the object. It accelerated at a certain rate. That rate times its mass tells you, hey, this is the force of the planet's gravity acting on that mass. Right? This is a good one. This is bringing back some old stuff we've done in the past. But we got to know gravity. This was like old school gravity, not the universal gravitation that we're going to talk about. Josh, you got some or okay. That's a good question, Maggie. What other ones do you want me to go over? Tricky ones. We can try to focus on more of the circular motion ones. Oh, number 14 was a doozy. That took me like 3 times to get that, to be honest.
That's reassuring.
It's a lot.
In my notes,
What?
I took like little notes when I was going through the answers, and I put close.
Close?
I was close.
Yeah, there's a lot of algebra on that one.
I don't even remember what it was.
I don't even know if that's worth my time.
I think it is.
You think it is?
Yeah.
Do you want me to show you,
Yeah.
or actually do it all?
What question? Oh, yeah. I remember.
Okay, I can try and... This one is a lot of algebra manipulation. So, it says there's a ball with mass m. It's a vertical circle. So it's swinging in a vertical circle. At the top, this is the forces at the top. So when the ball is at the top of that circle, these are the forces acting on. That makes sense, right? Gravity's always pulling down, and the string attached to the ball is still trying to tug it and keep it in a circle. That makes sense? This is the ball at the bottom. So when you swing it down to the bottom, gravity's still pointing down, just like we expect, but the string is pulling it back up. Remember, it's always pulling to the center of your circle. So I got these forces. They've drawn a free body diagram showing the direction of the force and the magnitude, right? Huge tension in the string at the bottom, but hardly any at all at the top. That should make sense, right? I need a certain amount of force to keep myself in circular motion, don't I? So let's do Newton's second law. What type of force is acting, the total force? Or actually, what kind of motion do I have? What kind of acceleration is happening if this ball is spinning? Centripetal. This is AC. Whoops. So it's got to have a centripetal force. Right? MAC. What is the sum of all the forces on this object? It shouldn't be a hard question. What forces are acting on here? Just look at it. Gravity and tension. Remember, this is when the ball is at the tippy top. Gravity's always pulling down, and the rope is also tugging down a little bit. So I need to add these two. This is force of gravity and tension 1. Tension 1 is the tension at the top. These two forces add together are the centripetal force that causes this ball to be in a circular motion. Right? Now I need to do the same thing over here. Let's do... Oh, wait. 1, 2 is MAC. This acceleration is the exact same. It's in the exact same circular motion. So, I need to add up all my forces. What forces are acting on this ball when it's at the very bottom? Gravity is pulling down, but the tension is pulling up. Why does this tension have to be so much bigger than gravity? Yeah. I need to keep pulling up. I need my force to go to the center of rotation to keep it in a circle. Well, gravity's pulling down. It's doing the opposite of what I want. So I have to have a huge tension to overcome gravity and then provide enough force to keep it in a circle. So then, this case, I'm going to do tension 2 minus gravity. Right? This is going to take away part of tension, and the remaining part of that tension points to the center of the circle and lets me go in a circle. What do you know has to be true about the total force in situation 1 and 2? It's going in the same circle at the same speed. I'm just looking at 2 points in the circle. Here's another question. If I have the same centripetal acceleration, aka I'm in the same circle, can I have different total forces? No. If this force was different, my acceleration would be different. The acceleration is the same at both positions, the top or the bottom. So that means this and this are equal. So you come over here and say, force centripetal 1 is force centripetal 2. Force centripetal 1 was Fg plus T1. The second force at point number 2 was T2 minus Fg. I got to simplify this. I got to add Fg over, so I get 2Fg is T2, got to subtract that over, minus T1. Right? Let's put it in terms of Fg. T2 minus T1 over 2. This is the tricky part. It's asking us, what's the acceleration? I want to know what AC is. Right? So, again, this is a lot of algebra. I got to go back to one of my equations. I'm going to do the first one. The centripetal force is mass times centripetal acceleration. Well, for situation 1, that was equal to Fg plus T1 is mass times centripetal acceleration. Right? This was F equals ma for this part. I'm going to rearrange that so I solve for acceleration directly. So to do that, I got to divide this Fg plus T1 divided by mass. That's equal to centripetal acceleration. Do you see how I just rearranged Newton's second law for this situation? This is where the algebra gets ugly. I know what Fg is in terms of T1, T2. That's what I'm trying to solve. I want to know what's the acceleration in terms of tension 1, tension 2, and then any constants. So I literally have to take this and say, okay, T2 minus T1 over 2 plus T1 all divided by m. Where's my... I need some more workspace. Then, it's a bunch of algebra. Right? If I change this to T1 times 2 over 2, that's still T1, right? I just multiplied by 2 over 2, which is 1. So it's the same, but now I have common denominators. So what's T2 minus T1 plus 2T1? Minus T1 and 2T1 is T1. Do you see that? All of that is divided by 2 all over the mass. Now, I need to simplify this. I want to get rid of this fraction. Or wait, I'm going to multiply by the reciprocal. Multiply by 1 over m to get rid of that. So my final answer is T2 plus T1 over 2m. Right? A lot of algebra. Not terribly difficult, it's just a lot of steps and a lot of algebra. Right? They force you to answer the question using certain variables, which forces you to do this and then plug back into an original and solve. Right? You have a system of equations. That one's weird, but you guys wanted to see it, so there you go. All right? Let me see if there's another one that I... You did the circular motion that I wanted to talk about. Yeah, a lot of this was friction, or gravity, excuse me. Here's a good one. It's a short one. It's a conceptual question. This one. Oh, God. That gives me a headache. This one is saying, hey, I collect some data near the Earth's surface. This student says, hey, this graph shows that the object is in free fall on Earth. Do you agree with that or not? How would we know if this is in free fall on Earth? The velocity over time, that can't help us. If we knew the acceleration, could we see if it's Earth? Yeah. Just do the acceleration of this object and determine whether it matches what we know is true of Earth. Well, if I do acceleration is change in velocity over change in time, the slope of this graph, my final position will do negative 40 minus 0 over 5 seconds to start with. Initially I was at 0 seconds. Negative 40 over 5, negative 8 meters per second squared. Does that match what we know is true of Earth? Do objects fall at negative 8 meters per second squared on Earth?
No.
Yeah.
No. What should it be if it's Earth? Negative 9.8. So this student's claim is wrong. They said, oh, this data shows it was dropped on Earth. No, it didn't.
Negative 8, does that make it go up?
No. Negative 8, remember we always think this is positive. So if it accelerates down, we call it negative.
Imagine
Reverse gravity. So you got to look through the answers and said, there's two options for no. AP will good or difficult multiple choice will always give multiple reasons. So it's not just like, oh, the answer is no. Oh, there it is. This one says no, the area under the curve says acceleration increasing. Wait a minute. Area under the curve for velocity time. Velocity meters per second times seconds gives me meters. The area under the curve is not in acceleration, so that's garbage. The only option is this. The slope of the graph indicates that acceleration is less than g. That indicates that another force is active. It's not in free fall. There you go. Any other questions about that multiple choice? Again, sorry, there was a lot of stuff you didn't know yet. Hopefully by the end of today, you'll be like, oh yeah, I know that now. All right, any other questions for the answer key? Multiple choice questions A. Are you guys able to retake it?
You might need to reassign.
Oh, okay. I don't know. I'll see. Anyway, that's all. I wanted to take time to review that. The next thing I need to do is talk about something called the fundamental forces. Has anybody heard of the fundamental forces of the universe? You've probably heard of them individually. This is a really minor topic. Why is that cut off? This is something that I just want to touch base on. There are 4 fundamental forces in the universe. One of them, you know, is gravity. Gravity is where 2 objects are attracted to each other. Any 2 objects. Everything with mass has gravity and will try to attract other objects with mass to it. The Earth has an enormous mass, so it has a lot of gravity. That's why it pulls everything down towards it. But technically, we have mass, and we pull the Earth up. But gravity is one of the fundamental forces in the universe. Another one you've heard of is electromagnetic. Positive and negative attract. Right? You got a positive proton and a negative electron. What do? They attract to each other. That's the electromagnetic force. Same thing is true if you have two positive charges. What do?
Repel.
Yeah, they repel. They push away from each other. The two other forces you probably haven't heard of is the weak nuclear force and the strong nuclear force. The strong nuclear force is what holds the nucleus of an atom together. You don't need to memorize this, just know basics. Strong nuclear force, that holds the nucleus of an atom together. The weak nuclear force, it's really, really weird. I'm not sure how to describe it, really. Talks about other particles called like bosons. It gets really nitpicky. Yeah, I don't know how to explain this in a generic way. It gets super physicsy really quick. So I really wouldn't worry about it too much. The one thing I really want you to understand, these forces are listed in terms of their strength. Strong nuclear force is top dog. By far the strongest force of all the four fundamental forces. Right? If you had a tug of war between strong nuclear force and any of these, the strong nuclear force would win. Number two is the electromagnetic, right? Positive, negatives attracting, or similar charges repelling. That's a pretty strong force. The weak nuclear force is the number three, and all the way at the bottom is gravity. Is this surprising to you guys? Gravity is literally the weakest possible force in the universe. If you compare the strengths, if the strong nuclear force is, a 1, an average, gravity is 0.00039 or 38 zeros and then 6. It's an unbelievably small fraction of the strong nuclear force's strength. Look how much the electromagnetic force is 137 times weaker than the strong nuclear force. This explains why gravity doesn't pull you to the center of the Earth. The atoms in my feet and the atoms in the ground, what swirls around outside of atoms? Electrons. If I have atoms in my shoe with electrons, and then atoms in the ground with electrons, what happens when I bring those electrons near each other? They repel. Those electrons between my feet and the ground repelling each other can stop gravity dead in its tracks. That's why when I jump, I don't go through the center of the Earth. The electromagnetic force, as soon as those electrons get close to each other, they repel. They stop the motion. They literally stop gravity dead in its tracks. It's crazy. This blew my mind when I learned how weak gravity is. It's pathetic compared to the other forces. What I want you to understand is, if you're going to look at a physics situation where you only consider gravity, you need to remove all these forces. These are fine. These happen at the atomic level. They don't really impact an overall object. But you would have to remove electromagnetic charges. Right? One of the questions, I think, was, number 13, it says, you have two particles, and you want to see where the only force is gravity. Which ones would you pick? Why is picking a proton and an electron a bad choice? If I only want gravity, why would I not pick a proton and an electron?
They attract to each other.
Yeah, I'd have electromagnetic charge. Well, then I'd get confused. I'd get both forces, I couldn't tell what's what. So the answer to that one was a proton and a neutron located a millimeter apart. Neutron has no charge. You don't get any of this, you get none of this, so you only get gravity. That's why I want you to be aware there's 4 fundamental forces. Gravity is by far the weakest. I want you to pay attention. It has infinite range. Now it gets really small really quickly, but gravity technically acts at an infinite distance. It just gets so small that it's almost zero. Electromagnetic force is the same way, but after a certain point you can ignore it. Alright? Any questions about the fundamental forces? Sometimes they're going to basically ask, like, what scenario would only have gravitational force? You have to think in your head, okay, I got to get rid of the other 3 forces. Mainly, that's going to be getting rid of electromagnetic. And know that gravitational force is the weakest, and it technically has an infinite range. Alright, we just needed to touch on fundamental forces. What else did I have? Oh yeah, universal gravitation. Okay, I'm going to try and go through this. Guys, can I have your attention? Trevor, Evan. All right, I'm going to go over gravitational force. This is the one, last missing piece that we have for this unit. All this is talking about the force of gravity at a universal level. Like an equation that you could apply to any object, not only on Earth, but anywhere. Our orbits are affected by gravity. The sun has gravity that pulls the Earth towards it. That's what keeps it in motion. How do I stay in a circular orbit? Don't I need a centripetal force? Mm-hmm. What forces act in outer space?
Sun, gravity.
The gravity. The sun has a ton of mass that pulls objects toward it. Well, every time I'm rotating around the sun's always pulling it directly towards itself, which keeps it at the center. That's why the Earth is not the center of the universe. Technically, the sun isn't either, but the sun's the center of our solar system because it's always pulling everything towards itself, keeping it in circular motion. Now, it's technically not a circle. It's like a slight elliptical, but there's something called universal gravitation. This is what we're talking about. Gravity gets weaker by the distance squared. So if you have gravity at a distance 1 away, your gravity strength is, say, 1. If I double my distance, the gravity strength doesn't go to 1/2, it goes to 1/4. It gets smaller by 1/r². Every time I double the distance, I exponentially decrease the force of gravity. If I go to 3 units away, my gravity is 1/9 what it was at my starting point. So it gets weaker and weaker. This is leading us towards the equation for universal gravitation. Guys, is there any way I can make this more engaging? Do you want me to get the lights back on? I got some of you guys sleeping on me. I know it's right after lunch. I know this isn't riveting, but we have to get through this. I understand, but I desperately want you to know this, so we know this for the test. I don't know any other way to get through this besides I got to show you what this equation is. So I need you guys to slap yourself awake. Right? We got a test. I'm trying to get you ready. So gravity is proportional to 1 over the distance squared. If you double the distance, you exponentially decrease gravity. Just know it gets really weak really quickly.
So is that multiplication?
This is proportional. gravity is proportional to 1 over the radius squared. We're going to basically get up all these pieces. If gravity, the acceleration of gravity decreases of 2 objects, the force is the same thing. Gravity's force shrinks by 1 over r squared. R is the distance from object A to object B that are having attraction. Gravitational force is proportional to mass. This makes sense. If I have something that's in free fall, and then I have another object that's twice as massive, I need to have twice as much force. It also makes sense. Gravity is the attraction of mass. If I have more mass, I have more attractive force, aka more gravitational force. So we also know the force of gravity is the same as mass. Increase mass, increase force. Decrease mass, decrease force. All right, we're going to have all these little pieces we're going to put together. Right? If I do 66 times my original mass, guess what my force does? It goes up the same amount. They're linear. They are proportional to each other. Well, if I have another planet that a second object is 318 times that mass, well, now my mass is this times this. It's much, much bigger than the original force of 2 singular objects. So in reality, the gravitational force is proportional to the 2 masses multiplied together. It doesn't just matter if I increase Earth's mass, the force will get stronger. But I could increase my mass, and the force gets stronger. So the gravitational force is proportional to the 2 masses multiplied together. What happens if we put them together? Well, gravitational force is proportional not only to the 2 masses multiplied, but also divided by r squared. We're basically at the result. This is our final answer. This is very important. All of you need to know this and memorize it. This is universal gravitation. This is the gravity of any 2 objects. Evan, are you with us? This is the key result. This is the force of gravity between any 2 objects. All we need to know is the mass of each object and how far apart they are from each other. G is a constant. We'll always know that. Did everybody get that? Nope. Yeah, this is super important. It's the gravitational force, the attraction between any 2 objects. Don't care what they are. If it's an object, it has to have mass. So it applies. It has gravity. Now, if I go one more, this is what G equals. That capital G, that constant, it's called the universal gravitation constant. I don't think you need to memorize this. I think this is on your... Yeah, it's on the back side of your equation sheet. It's really weird. It's G is 6.67 times 10 to the negative 11 meters cubed over kilogram second squared. Basically, those units are so that when you calculate this, your units come out to newtons. So the units here are kilogram or meters cubed over kilogram second squared. Meters cubed over kilogram second squared. The way that they found this is they did experiments, right? They have 2 balls, 2 large ones, 2 small ones, and they figured out how attracted to each other are they, and they measured that force, and they do math backwards. You don't really need to know this. I just want to show you. They were measuring the angle, how much it moved, how much those objects were attracted to each other, And when they did, it would change the angle of the laser. They measure it, plug in the numbers, and back calculate. Whoops. They back calculated all this to find G. This is the same anywhere in the universe. Doesn't matter if you got two planets. Universal gravitation always works. Mass of the Earth. That's a lot of kilograms. Do you understand why it's so difficult to escape Earth's gravity? It has such an enormous amount of mass that it has enormous force that's always acting on us. It never gives up. So what they did is they used this universal gravitation to calculate. They know if you're on the surface of Earth, you're a distance of 6 million meters from the center of the Earth. So the Earth's radius. So I could plug that in. I know my mass of object 1. I know universal gravitation. And we can experimentally calculate the force. This is F equals ma. The force on this object from gravity is mg. 1 kilogram times 9.8 gives me 9.8 newtons. I'm going to just do my math and figure out what Earth is. This is how they figured it out. So they did their math. So a lot of times they're going to say, hey, you and this planet are this far apart and this much attracted to each other. What's the mass of that planet? We just plug it in, find your unknown. They might ask you, you and a planet have this mass and are a certain distance apart. How attracted to each other are you? Just plug it in and find it out. Right? Sorry, I don't know if I can get that changed. Another weird point, everything is attracted to everything else. So it's a weird example. This woman and this man are attracted to each other. Gravitationally. I have no idea if they're romantically interested in each other. But in physics, you can say that everything is attracted to everything else. It is an absolute certainty. We've determined that. The amount of attraction depends on the two masses of the two objects and how far apart they are. And you can calculate it. So if you do the math, they're, like a millionth or a billionth of a Newton. So if you have two people attracted to each other, or standing next to each other, you can calculate how much attraction there is. It's really small. I want you to pay attention. If you change the radius, you will drastically start decreasing the force. Right? If you pull people apart, the force will drop by r squared. It will drop exponentially. If you increase the mass, it will increase linearly. One increase in mass is the same increase in force. But an increase in the distance changes exponentially. It'll decrease exponentially. Any questions? Again, just introduction to universal gravitation. Really, it's just that equation. Force of gravity is capital G, m1, m2 over r squared. Any two objects are gravitationally attracted to each other. So, I want to go straight into application. The biggest thing is orbits. Planets in orbit, they are in orbit because they're in circular motion, correct? What force can cause or create circular motion in outer space? I don't have strings attached from planet A to B to twirl it. Well, yeah, anyway. There's no friction. There's no applied force. The planets aren't in contact with each other. What force can possibly keep it in motion? Gravity, thank you. All objects are attracted to each other. We orbit the sun because the sun is constantly attracting us as we go around it. So you're going to combine circular motion and gravitation. Orbit. You know, remember we talked about this a little bit? The time it takes for one rotation, that's called the period. The period of the moon is 27.3 days. To make one full rotation, the moon takes 27 days. That's the moon's period of orbit. Now we use satellites in orbit to do GPS, location services, GPS, right? We have satellites that orbit the Earth so that we constantly get signal, right? What keeps that satellite going in a circle? The Earth's gravity. And also the satellite's gravity to the Earth. This is where you also get Newton's second law. If the Earth pulls on me, I pull back. Just as much as the Earth is attracting me, I'm also attracting the Earth. But my force applied on a huge Earth is almost nothing. But the Earth can apply that same force on little tiny me, so it can really make a difference. So there's an equal and opposite. But again, the Earth's mass is so big that it almost is unaffected. Right here. The screen is driving me nuts. Whoops. This is in circular motion around the Earth. Right? What force keeps it in motion? What force is always pointing to the middle? Gravity. The gravity is the centripetal force. Well, centripetal force is mass times acceleration. Gravitational force is the universal gravitation. And I can equate those, start simplifying. I don't need you to know this. Just know that you can do basic Newton's second law and find the period of orbits. Really easy. I don't really need you to know this. I just need you to see that you can start with what you know and then just do algebra to get somewhere. Right? You can all do this step, correct? You all should be able to do this. Does that make sense? Centripetal force is ma. Centripetal acceleration is v squared over r. We know that. We also just learned the force of gravity can, in its simplest form, is g/mm over r squared. You all can do this, and then you can do algebra, away you go. I don't care about the rest of it. Space elevators are something we want to do. I don't think we're ever gonna. This is sort of like an orbit. Remember we did an example of this? You're on that swing and it gets you spinning. The faster you go, the more tilted you are. Right? You are orbiting the middle of that carousel or whatever. Right? But in that situation, you got tension. You don't just have gravity. But it's still circular motion. I don't like this example. The other thing that we need to talk about is gravitational fields. Remember I told you gravity acts over an infinite distance. So Earth has this infinite field that spreads out, and anything in that field is influenced by Earth's gravity. I have a gravitational field. It's really weak because I don't have a lot of mass, but I'm attracting everything to me. And the further away from you get, that force of gravity gets weaker. Gravitational fields are a way of describing the space. It's a property that space will put force on other masses. Gravity's acting everywhere. Any sort of mass in the field experiences the force. No force, no field. No field, no force. Yeah, the force, the gravitational field is basically where gravity could act. Well, it spreads out infinitely. So technically that gravitational field is everywhere. Everything around me is in my gravitational field. It's just you're so far away that the force is so weak. Nothing really happens. But the sun's gravitational field, it spreads infinite too, but it is very strong. So even though the Earth is, 93 million miles away, we still are sucked into orbit constantly by the strength of the sun's gravitational field. Gravity itself, gravity is space. Like if you turn to like space-time, the fabric of the universe, that kind of a thing. Gravitational field is G. Essentially, it's the acceleration. That is the strength of the field. It relates the force of gravity divided by the mass of the object. Has any of you seen diagrams like this? This is saying gravitational field acts like this big funnel. The Earth in the middle causes an indent in the funnel. Whenever a planet is in that field, it wants to roll towards the Earth. Well, if I'm way out here, I'm not really going to roll hardly at all. There's almost no incline. Technically, that incline goes forever. So anywhere, I'm always going to be rolling a little bit or pulled a little bit towards the Earth. If I get close to Earth, I'm going to get sucked in real quick. That's why we can't escape. Yeah, imagine if you would have to climb up this hill to crawl away from Earth. We are so close, we're at Earth's surface, we can't even go anywhere, right? That's as best as we can do. Right, you can.
Then you can get like rockets. And you
Yes, you can, but you need a rocket to escape this gravitational field. The field is the strength of the gravitational force per unit of mass. Do you see this? The strength of Earth's gravitational field at one radius away, aka on surface, is 9.8. We know this. This is gravity on Earth's surface. The strength of gravitational field. However, if we get high up in the Earth's atmosphere, so we're 2 radiuses away, G is not 9.8. We have gotten further away from the center of Earth, so its field strength is weaker. This is why technically, if you're a weight trainer, if you're a professional bodybuilder or professional, like world's strongest man, technically you would want to train at the lowest possible elevation. Why? Yeah. I'm closer to the center of Earth, gravity is stronger, so my 100-pound weight actually feels like 110. I can get more resistance and train more. Well, then I'm going to travel across the country, and they're 1,000 feet higher than I am. So my 100 pounds, it's going to feel like 90 pounds to me, because I train with 100 pounds at a low elevation, and it's heavy. I have to work to get it.
So
if I go to competition, I can rep that out like no problem.
So if you went to like the lowest point,
yes,
you possibly go, like 100 pounds, you feel like way more.
No, it would not feel like way more. I'm exaggerating. Again, you change 1,000 feet, the Earth's radius is like millions of kilometers.
Okay.
Or wait, maybe it's like tens of thousands.
Because I was thinking of like,
it's a small change.
There's that really like deep
Death
trench,
Valley.
That trench.
Oh,
that's in the
what is it, the
ocean
Mariana Trench or something?
like that.
Yeah. So again,
theoretically, I'm saying like if you were that like
yes,
deep
theoretically.
Theoretically, if you be that like deep, that does that mean that it would just be like it would feel like a lot more?
It would feel like a lot more. You would have to go a significant distance to make it actually make an effect, because Earth's radius is huge. But I just wanted to give you an example. The closer to the center of Earth, the stronger the gravitational field. If you go out further away, remember that bowl analogy? If I go further away, the slope, the strength of the pull gets weaker. I just want you to be aware of that. Because I'm changing this. I'm changing my distance. All right, I don't want to go through this. The last thing, inertial mass is F equals ma. Inertial mass is you have a mass, you apply some force and get the acceleration. It's the mass of an object, you put it into motion and find the mass. Right? We apply a force to figure out the mass. Gravitational mass is scientifically determined to be exactly the same as inertial mass. It's mass, but it technically is coming from what's the force of gravity? Gravitational mass is the mass we use considering gravitational attraction. Inertial force is if we put that object in motion and measure its mass. In reality, those two have been determined to be the same. They are different, but we've determined they're actually equal to each other. Does that make sense? Inertial mass is your mass. It's your resistance to motion. Inertia. Inertial mass. Gravitational mass is your mass in regards to gravity. How attracted am I to the Earth? That's my gravitational mass. Turns out it's the same as your inertial mass. They're different, but determined to be equal to each other. All right, so the last thing I have for you guys is hopefully a quick lab on gravity force. So I want you guys to get out your computers. It's a PhET simulation. It's pretty cool. You bet. Oh yes, thank you. If you guys have homework for me, get that into me now. Otherwise, your last time to get it in will be when you walk into class. Well, I guess like halfway through class on Friday.
Where did you get this from?
I just give you one, right?
But
I don't know what I'm doing.
Are we gonna watch the TED Talk?
Yes, I will play that video right now. First thing I'm going to do is play a video that kind of helps explain gravity. Oh, sorry.
Lucky you.
I'm going to crank this up.
John. Speaker.
Get this guy going. There we go. All right, this is basically to start you off for the lab.
So what is gravity? I'll bet most of you think it's what goes up must come down.
It's a little cheesy, but
Is
roll
that
with
right?
it.
Well, sort of, but not really. Technically, the law of gravity is an equation. It is F equals G times M1 times M2 divided by R squared, where G is the universal gravitational constant, M1 and M2 are the masses of the two objects, and R is the distance between them squared. That was easy, right? Probably not. What does this actually mean? Well, it means that, well, everything is attracted to everything else. And what I mean by that is that if you have two objects, any two objects, they are attracted to each other. Okay, let's try and wrap our minds around this. What happens when you drop a rock off a cliff? It falls to the earth, right? Well, yes, but something else happens. You see, the law of gravity says that both objects, the rock and the earth, are attracted to each other. This means that the rock falls towards the earth, and the earth falls towards the rock.
Be looking at questions
Wait
1
a
and
second.
2
You
during
mean to
the
tell me
video,
that the earth falls up to meet the rock?
especially the
Yes,
equation at
exactly.
the end.
And the reason you don't see the earth fall up to meet the rock is because the objects move towards each other proportionate to their respective masses. The earth is much, much, much more massive than the rock, so it moves a very, very small distance. And the rock is much less massive, so it moves farther with respect to the earth. Maybe a better way to understand gravity is to take two teenagers in spacesuits and place them far out in space, away from all the planets and the stars. It turns out they will be attracted to each other. I'm not talking about that kind of attraction. See, they have mass, and since they have mass, they will move towards each other. They are attracted to each other. Maybe one more thing might help. Have you ever played with two magnets? You know the magnets with the north and the south poles? When you take the magnets and put them closer to each other, they move together. They are attracted to each other. And the closer they are, the stronger the attraction. Think of the mass of the object like the strength of a magnet, and the distance between the objects like the distance between the two magnets. Now understand, I'm not saying that gravity and magnetism are the same. They just behave in a similar way. Let's think of one other thing. Astronauts. You know, astronauts, they weigh less on the moon than on the Earth. Why is that? Well, you see, the moon is less massive than the Earth. Therefore, it has a smaller gravitational pull on the astronaut. It's like the moon is a weaker magnet. They aren't as attracted to each other. Distance also plays a role. Think back to playing with a magnet. The pull of the magnets towards each other are stronger when they are closer together. The same is true of gravity. For example, the sun is the most massive object near the Earth. It dictates most of the gravitational forces in our solar system. It is very, very massive. But it is relatively far away, so even though the sun is a much stronger magnet, so to speak, it is a long ways away. Therefore, the attraction isn't as strong. So let's look back at that law of gravity, the equation. F equals g times m1, m2 divided by r squared. You see, the force of gravity is equal to a number, that universal gravitational constant,
this one
g,
we learned about.
times the mass of object 1 times the mass of object 2. Think of m1 being the mass of the sun, and m2 being the mass of the Earth. And then we divide by the distance between them squared. This determines the force of attraction between the sun and the Earth. You could just as easily plug in your mass and the Earth's mass and the distance between you and the center of the Earth, and find out how much you are attracted to the Earth and the Earth attracted to you. So what's gravity? Everything is attracted to everything else. Everything. Oh, one last thing, just to make you wonder. What causes gravity? Why are two objects with mass attracted to each other? Well, the answer is, we don't know. The cause of gravity remains a mystery to scientists. We don't really know conclusively what causes gravity. It is one of the great mysteries of science.
Okay. So this was the equation. So when we look at this equation, question number 2. I'm gonna try and help you with this. I didn't give you a lot of time. Question 1, I'm gonna have you jot down your thoughts on your own. Right? How would you define gravity? Really short, in your head, what is gravity? After hearing about it, watching this video, just jot down for me, what is gravity to you? Real short, real sweet. That second question, what's the force of gravity, aka the law of universal gravitation? That's what this is. So you should have this equation down. We should be able to do this, but what's the units of force? Newtons. The radius, the distance between two objects, what's the units here? Meters, but meters squared. Stop. Mass here, kilogram, mass, kilogram. Now we got this guy. Meters cubed.
Oh, it is
Yes. So G is meters cubed. What was it over?
kilograms. Seconds.
Yeah. Do you see how this works out? One of my kilograms goes away. I got meters squared, so this is just meters. Well, what I'm left with is kilogram meter per second squared. You guys remember? That is what a Newton is. So I want you to see that the units here are ugly. Meters cubed per kilogram second squared. Kilogram, meter squared, newtons, we know that. But I want you to see they work. This is the only new one. All right, that's question 2 on your lab. Then, I'm going to go through this with you a little bit. Feel free to have it open on your computer as well. But I kind of want to do this with you guys right now. So, what can I change about the lab? What can I change? We need to make a list. I can change the sound effects are the weirdest thing ever. Why would they need to add sound? I don't get it.
Sounds like a cable.
Yeah, so I'm going to mute that. Okay, what can I change?
Keep it on.
Mass of the two objects.
I can change mass of the two objects. I can change mass 1. I can change mass 2. Can I change the distance between them? Yeah, I can change the distance. Can I change anything else? No, right? Doesn't that make sense from our equation? I can change the mass of two objects and the distance between them. The universal gravitation, capital G, it's always the same. And then whatever those are determines the force. I can't change the force unless I change the mass or the distance. Is that you? No. It was actually very convincing. I did question if I muted or not. Okay, second question. Examine the formula for the force of gravity. What 3 things can you change in the formula that you could also change in the simulation? It should be easy.
The mass of object 1, the mass of object 2, the distance.
Bingo! This simulation is showing just a generic gravity situation. The only things that you could change is the mass of both objects and how close they are. Anything else I don't care about. It doesn't affect gravity.
Wait, so it's object to mass 1. I mean, mass of object 1, mass of object 2.
And then the distance, which is r. In the equation they call it r. The distance from... So I could change the size of this, and it wouldn't matter. Right? I could keep the size the same, but change the mass. The size doesn't matter. The only thing that matters. Mass 1, mass 2, and the distance. So, change, number 3, change each variable and record what happens. Do you see how the force on mass 2 from mass 1 is the same as the force on mass 1 by mass 2? Newton's third law. Every action, there's an equal and opposite reaction. They attract each other. What happens if I increase the mass? Stop. God. What's happening to the force as I increase mass? Oh, let's do mass 1. What happens to the force? We need to get through this, you guys. It increases. Thank you. So you need to write M1 increase equals F2 increase, or F increase. If I increase mass 1, the force increases. It's at 4 million now. What happens if I increase mass 2? F increases. So you're going to write increase in mass 2, increase in force.
I just wrote M1 increase.
Yeah, that's perfect. Yeah, just say M2 up equals F up. Right? What happens if I increase the distance? Force goes down. They're inversely proportional. If I increase distance, I decrease force. That also means if I decrease distance, if I bring them closer, look how big that force is.
Huge.
Crank it up. Yeah, they go off the chart. 11 million newtons. Right? Does it make sense from our equation? Stop. Oh, you're playing it. I thought you guys were doing that with your voices. I was like, wow, that's really accurate.
Oh, no.
You tricked me twofold. I thought you guys were saying it as I was moving, but I didn't realize you were moving it the same as I. You got me good. Okay, but I want you to see mathematically. If mass increases, if this number gets bigger, this number gets bigger. We're on the same side of the fraction. However, if this gets bigger, this is a smaller fraction, so this goes down. Do you see that mathematically and experientially, I guess? More mass means more attraction, so a bigger force. But if I pull them apart from each other, the force goes down. Right? That's what number 3 is all about. So this one is kind of tricky. What data would you need to calculate G? Yeah, what data would you need to figure out what this is? Literally look at this equation.
Just between the mass of two objects.
And the force. This is universal gravitation. If I know all these things, I can calculate that. Right? So your thinking question, what data do you need? You need, you need F, M1, M2, and R. That's what data you would need to find G. How could you put that in Excel? Just give me a super basic answer. Could you use Excel to calculate this? Like a spreadsheet software? Could you collect data where I say, okay, mass 1, mass 2, and a distance? I tell Excel, hey, calculate this times this squared, and then divide that number by force, and tell me what gravity is. So basically, I want you to just write, plug in known values, and calculate in Excel. Because you would just put your data in, and then write a formula that says this times this divided by this times this equals this. So number 2 on the back side, just put known values in Excel and calculate G. Now, unfortunately, we don't have time to do this. So cross out section 1. Question 1 on the bottom side. If we don't have time, I apologize. Do you think, number 2, how close is it? Write in, what do you think? Would it be really close, not even close, or exact? If you're collecting data yourself, what would you say? Is it going to be pretty close? Is it going to be not even close? Pretty close, right? So number 2, tell me, I'm cutting this short for you guys. Pretty close is a good answer. I'm going to have you cheat a little bit and just say, how close was it? Well, it was pretty close. If we collected data ourselves, we'd get pretty close. What would make it pretty close and not exact? Why couldn't we get exactly G? What?
Human error.
Error, right? Oh my gosh. We need to not do that, all right? That's going to get real old real quick, okay? So human error, right? I could measure the wrong mass, right? I could have an incorrect procedure. Another possible reason is device error, right? My scale only goes to the thousandth of a kilogram. Well, really, I would want as accurate as possible to do my calculation. I could also have a rounding error. If I round my mass up to like the nearest 10, so it's 9 kilograms, I round to 10, boom, I just introduced error. Can I measure my distance exactly? No.
So human error or math error?
Yeah, math error, system, like measurement error, right? We only have devices that are so precise. So now the last question, if you've seen kind of a simulation, did your definition of gravity change? If not, just repeat what you put at the beginning. But question 4 is like, hey, how would you define gravity? Define gravity. Describe it to me. If a middle schooler asked you, hey, what's gravity? What would you say? It's actually really difficult to simplify something. If you know something very well to the point where you could simplify it to someone younger or less experienced than you, you really understand that topic because you know the core concept and you can reduce it in a way that someone younger than you could understand. So think about it in that terms. What were some of your guys' can some of you share what you said for like how would you describe gravity? Like genuinely, I want to know what are some things you said.
The force of attraction between two objects.
Boom, I like that. Because he said two objects. Doesn't matter what two objects, right? If something is an object, it has mass. Therefore, it has gravity. So that's a great answer. Any other different ways to phrase it?
It said the force that every object with mass has that causes it to move towards any other object with mass.
Nice. I like that. Any object with mass has a force that causes it to move towards something else. Any other descriptions? Okay. So again, I apologize for running out of time. I need you guys to write your names on these. Make sure your names are on these, and I need those turned in, okay? I need to give you points for these. Yep, I want those right now. Yep, virtual students, you should have been able to follow along with us and filled this in with us. I want you to just take a picture, or you have an electronic copy that I'll give you. You could just type in your answers if you want, but I need you to submit that on Classroom, like today or tomorrow. Then I can give you lab points, right? So everyone should get 100% on this lab. Where we're going next, next class, we're going to spend the first third or half final review. Talk about big ideas, right? Make sure we're all on the same page, we all got stuff down, and then we'll take the test the very last part of class. Please, if you have missing work, it is due next class. Don't let it be stuck at a 0. If you get it done tonight, send me an email like, hey, Mr. H, here's my homework that I didn't turn in. I'll be like, great, I'll update it in Power School, good to go. All right, I want you to, if you really want to practice, take B. The AP, there's multiple choice B. I posted that. Take that if you really want some practice. Otherwise, review your notes and review the big ideas on Classroom. That's that's fine. Thank you, guys. Thank you. Again, sorry I kind of
Miss Sharamatero, please come to the office. Miss Sharamatero, please come to the office.
We'll review the first part of class, and then we'll take that test.
Caleb McFerrin, please come to the office. Caleb McFerrin, please come to the office.
Thank you. Got yours? Okay, just bring it back to me next time, and I can still give you points. Yeah, thank you. I got yours, Aiden?
You win a bit fast. So,
I'm sorry, I thought we were all on the same page. How far did you get?
It's okay.
Yeah, but do you remember, Again, I kind of cheated. You don't actually do it. Just describe what you do. Does it make sense?
Mr. Ray.
So I apologize for going so fast.
I'm running to the bathroom.
What's that?
I'm running to the bathroom.
Okay. Hustle. Yeah, that's fine. I apologize. I was trying to get things done. But what you do is make sure you give it to me next class, and then you can get full class. Yeah. But that's no problem.